Hello, my name is Davis Binger, and let's talk about the solution to quiz number 3. Quiz number 3 had an in-class problem and a take-home problem. The in-class problem asked you to find the length of the curve y equals e to the negative 2x plus 1 over 16 e to the 2x on the interval from negative 1 to 1. The take-home problem considered a tank formed by revolving the curve y equals 4x squared on the interval from 0 to 3 about the y-axis. The first part of the take-home problem asked you to find the volume in the tank once the tank was filled to a height of h. The second part was a related rates problem. It said if the tank is losing water at a rate of 2 meters cubed per second, what is the rate of the level of the water is falling when the level is at 1 meter? The third problem asks you to put 20,000 kilograms of water into the tank and then to determine what height those 20,000 kilograms occupied. The fourth problem said once you've put those 20,000 kilograms of water into the tank, how much work is done taking it out of the tank? Alright, let's start with the in-class problem. So we have an arch, and it's modeled by the function e to the negative 2x plus 1 over 16 e to the 2x on the interval from negative 1 to 1. So just recall the general arc length formula for a differentiable curve. F from a to b is given by the integral from a to b of the square root of 1 plus the derivative of f with respect to x squared integrated with respect to x. So in this case it's easy to see that a is equal to negative 1, b is equal to 1. We have our function, and we can take a derivative of our function to find that f prime is negative 2 e to the negative 2x plus 1 over 8 e to the 2x. So I've reproduced this here, and we will perform a little bit of algebra to calculate what 1 plus f prime of x squared is. So I've just plugged it in, expanded the polynomial here, or polynomial and exponential functions, and the middle term is 2 times the first term times the second term. So we have 2 times 2 e to the negative 2x times 1 over 8 e to the 2x. And this turns out to be a half because the e to the 2x cancels with the e to the negative 2x. And it's 2 times 2 times 1/8. Times one of the 2's is negative. So we get a negative 1/2. This cancels with a 1 in that we're adding in, and we get 1/2. So recall that 2 e to the negative 2x times 1 over 8 e to the 2x times 2 is equal to a half. So this is actually a perfect square. And it is 2 e to the negative 2x plus 1 over 8 e to the 2x squared. Now, I've reproduced that equation here, and we can plug this into our length formula. We're going to integrate from negative 1 to 1 the square root of 2 e to the negative 2x plus 1 over 8 e to the 2x squared with respect to x. Note that e to the x is always a positive function, so under the square is always positive. So we can cancel the square root and the square, no problem. And we're left integrating from negative 1 to 1, 2 e to the negative 2x plus 1 over 8 e to the 2x with respect to x. So this is just negative e to the 2x plus 1 over 16 e to the 2x evaluated from negative 1 to 1. And after a little bit of algebraic simplification, this is 17 over 16 e squared minus e to the negative 2. This concludes the in-class problem. Let's look at the take-home problem. We have a tank, and we have this curve. Y is equal to 4x squared for x values between 0 and 3. And we're revolving this curve about the y-axis. So we're creating a parabolic bowl. Now, the first part of the problem is to asks us to find the height, find the volume once we've filled the water up to a certain height. And we're two choices. This is a rotational bodies problem. We're revolving the region bounded by the curves y equals h, x equals 0, and the curve y equals 4x squared about the y-axis. So those three curves bound a region, and we can revolve that region around the y-axis. So we can either use shells or washers to find the volume. Now, since we're revolving about the y-axis and our function is given in terms of x, one might think that the best option would be shells. But I've worked problems like this before, and I know that we will need the cross-sectional area, the horizontal cross-sectional area, to do the work problem in the final part of the take-home problem. And it turns out that the discs or washers you get using the washer disc method, those are the exact cross-sectional areas that we're interested in for the work problem at the end. So we're going to save a little bit of time now, and we're going to calculate this volume using the washer disc method. So we need to integrate with respect to y, since we're revolving about the y-axis, and so we need to solve our function for a function of y. It's a simple matter of dividing both sides by 4 and taking a square root, and we get x is equal to the square root of y over 4. So we need to figure out our bounds. The lower bound will be 0, since the liquid exists starting at a height of 0, and the liquid exists up to a height of h. So the volume will be pi times the integral from 0 to h, the radius squared. Now in this case our curve is here, and the radius is given by the square root of y over 4, which is just y over 4. And we integrate from 0 to h, we get pi y squared over 8 evaluated from 0 to h, which is h squared over 8 times pi. So that solves the first problem. Now, second problem, related rates. This may make you check back to your Calculus 1 textbook or look back in the notes to understand how to solve a related rates problem, because that may not be something you've done recently. But we should know how to do it, and so recall that if we have a relation between two variables, and we want to know if one is changing at a certain rate, how does this affect the rate of the other one? Well, you differentiate the relating equations. In this case, volume is equal to pi over 8 h squared with respect to t, and then you can plug in your rates and your pertinent information to find out what the other rate is. So in this case, we have v is equal to pi over 8 h squared. We differentiate that, we get dv dt is equal to pi over 4 times h times dh dt. And this is a nice relation. We just plug in dv dt is equal to -2, and it said what is the rate, the level of the water is falling when the level is at 1 meter. So you plug in 1 for h, and then you solve for dh dt. So this is just -2 times 4 over pi, which is just -2.55, approximately -2.55. So that takes care of problem B, and we're looking at problem C. We're told that water has a certain density, and we're going to find how full the tank is, what is the height that it's filled up to. If we put 20,000 kilograms of water in the tank. So volume times density is mass, and we have 20,000 kilograms of water, which means we have 20 cubic meters of water. So by part A, we said that the volume is equal to pi over 8 times h squared. That was by part A. So we just need to solve this equation for h after plugging in 20 cubic meters. you get the square root of 20 times 8 over pi, approximately 7.14. For part D, we've filled up the tank with this 20,000 kilograms of water, and we're going to calculate the work done draining that water out of an exit pipe at the top of the tank. Now note that our tank is 36 meters tall. How do I know that? Well, it's formed by the curve y equals 4x squared for x values between 0 and 3. At x equals 3, this function 4x squared obtains its maximum value, and this maximum value is 36. Thus, the max height of the tank is 36. So if we have a cross section that's at a height y, it will need to travel up to the top of the tank, and the distance traveled will be 36 minus y. So our work will be the integral over where the water exists. In this case, we integrate from 0 to the square root of 20 times 8 over pi. Remember, that was the height that if we poured 20,000 kilograms of water into the tank, that water reached up to. And we have density, which is 1,000, times gravity, times our cross-sectional area. Now our cross-sectional area is pi r squared, where the r is the square root of y over 4, and the distance traveled is 36 minus y. So that's our integral. We pull out our constants, get 9,800 pi times 1/4, integrated from 0 to the square root of 20 times 8 over pi, 36y minus y squared, integrated with respect to y. We just apply the power rule and evaluate on our bounds, and this comes out to approximately, 6 million some odd joules. Alright, that's the last problem. Thank you for watching. Have a good evening, and as always, you can reach me at binger@math.ohio-state.edu or by leaving a comment below. Thank you. Have a good evening.